Hi students, welcome to my class. So in this class, we're going to study a topic that is fundamentally important in our calculus curriculum, differentiation. So we will first define what is differentiation, which will be then applied to simple calculation. So before moving on, I'd like to brief some related history. So the invention of differentiation is credited to two guys. The first guy, Isaac Newton, who most of you guys may be quite familiar with, right? Another guy on the right, Gottfried Leibniz from Germany, who most of you guys have never even heard of, right? So Newton, in his physics study, Leibniz, from the perspective of mathematics, almost simultaneous but independently invented calculus, including differentiation. Okay. So even until today, there is a very big controversy as to who was the first guy to invent differentiation and calculus. Okay. So in the following, we will follow the path of Newton. That is physics approach to define what is differentiation. Okay. So we start with an anecdote which says that one day Newton at his property, as young as you guys, was sitting under an apple tree when suddenly he saw an apple falling from the tree. You know, Newton was a genius, right? He was very curious. And here is what he was thinking. Okay, the apple can fall to the ground. Okay. There, also our head is the moon, right? Why doesn't the moon never drop to the ground like the apple? Why does the moon always keep being there in the sky? So this curiosity kick off Newton's physics exploration. And after many years of arduous study, he discovered a groundbreaking law in physics. That is the universal law of gravitation. So, which says that the gravitational force between two objects is in inverse proportion to the square of the distance of the two objects in question. So it can be realized in a coordinate system like this. And as you can see from the graph, when the distance changes, increases, the gravitation decreases, right? And moreover, at different point, the gravitation changes differently with respect to r, right? The distance. So, for example, at this point, when the distance is small, right? The gravitation changes rapidly. But when the distance is very large, then gravitation changes very slowly, right? So a question naturally arises. How can we mathematically characterize the differences in change on the curve? Now, again, Newton, he was a genius, right? Now, he studied from the simple case, the straight line case. Now, given a straight line, intuitively, it changes evenly at different point, right? Now, given if we fix a point, now Newton pick another point, and he defined the gradient at this point to characterize the rate of change at this point, right? Which is defined like this: the rise around. That is, he used the y coordinate change over x coordinate change. So a question naturally arises. Okay, is this definition mathematically rigorous? That is a definition of gradient depend on the point we choose. Okay. Okay. Luckily, it will always the gradient will be always be unchanged, which can be proved through a use of similarity in triangles, right? Now, so this way to characterize the change, the rate of change, that is the gradient, is mathematically justifiable, right? So Newton tried to generalize the method to an arbitrary curve. Now, given an arbitrary curve, obviously at different point, the curve can differently, right? So if we fix a point, now, can we, okay, like in the straight line, just pick another point and use this second line, the gradient of second line, to define the gradient at this point? Okay, can we? Okay, this time it doesn't work. This method can't be transferred. Why? Because this gradient is dependent on the point on the curve we choose. If we choose another point, we then get another second line, right? And the gradient usually change, right? So this this way can't be used to define to characterize the tangent, the gradient at this point, right? Now, here's a thing which turned to be very groundbreaking. Now that you can't use the gradient of second line to characterize the gradient at this point, right? Now Newton, he used the gradient of tangent line at this point to describe the rate of change at this point. Okay, so okay, now here's a question: can we calculate the gradient of the tangent line? We know that in this case, we need at least 2 points to calculate, to figure out the gradient of straight line, right? But here we have only one known point, which lies on the curve, right? Because the curve is known, so this point is also known, right? So we have only one point on this straight line, right? Which means that at this moment, we can't calculate the gradient at this point, the gradient of tangent line, right? So now again, Newton, he was very innovative. Now, still he studied from a simplest case. He studied with a curve, okay, which you guys are familiar with since your childhood, since your primary school stage, right? So for this circle, which is curve, right? He pick a point on circle and he draw a tangent line at this point. And now he want to calculate the gradient of the tangent line, right? Now, now Newton studied his famous circle sort experiment. Now he drew a string of line parallel to the tangent. All of these lines cutting the circle at 2 points. So these parallel lines are all second, right? Second line rays, right? And we got a lot of chords, right? Chords. And if and we found some interesting things. The first thing is as the second line get closer and closer to tangent, the chord are reduced to a point. And second, the length of these chords get closer and closer to zero, right? So from this experiment, Newton extracted two things. The first thing is tangent line can be studied through second line. The second thing is limit is limit. We can use limit to study tangent line, to calculate the gradient of tangent line, right? Now, Newton returned to the original curve. Now for an arbitrary curve, now pick a fixed point on the curve C, f of C, and draw a tangent line at this point. And now, as in this experiment, Newton he drew second line, but he let the second lines passing through the point CFC. For example, he pick a point C plus delta x, f of C plus delta x. Here, delta x means the change of x coordinate, right? And for this point, okay, he connects the 2 points, C, f of C, and this point, right? And he get a second line, right? And now the second line is mathematically approachable. Why? Because the two lines both land on the curve, which is long, right? So the 2 points are long. So we can calculate the gradient of the two curves of the tangent of the second line, right? Now, if we pick another point, we get an arbitrary and a corresponding second line, right? And like the previous calculation, we can figure out the gradient of the new second line, right? Okay. So the next step, okay, he let the second line get closer and closer to tangent line. That is to say, he let delta x get closer and closer to zero. That is let the x coordinate get closer and closer to C, right? That is, he let delta x get closer and closer to zero. And then he apply a limit operation. Now, let's sum up, okay? First, for fixed point on the curve, first, he draw second line and calculate the gradient of second line, okay? Gradient of second line, right? Which is rise or run, and which is a change in y coordinate or change in x coordinate, right? So change in y is f of x plus delta x minus f of x, right? Change in x is delta x, right? Okay. Now, the second step, he applied limit operation, okay, to delta x. So, as a matter of fact, when the second line get approach to this point, right, the fixed point, to the tangent line, right, delta x coordinate get closer and closer to x, right? So the change of x coordinate, which is delta x, approaches zero, right? So we have this notation, right? Okay. So depending on your convention, some guys prefer to use h to denote the change in x coordinate. Okay, it's only a matter of preference. So if you use the H as a convention, then the second becomes like this. Becomes this delta x change into H. Okay, so and here the limit is with respect to H. Now, the above process of finding the gradient of curve is called differentiation. Let's recall. It includes two steps. The first step is you draw second line and calculate the gradient, right? The second step, we let the second line get closer to the tangent line, right? And we use limit operation, right? So the two step is called differentiation. Now, if we calculate differentiation at a fixed point, then we get the derivative at that point, right? We get the differentiation at that point. So in this case, it's called the derivative of fx at that point, denoted by f prime of c. Now, in general, the function, if at a point f on the curve, right, we can as okay, in this way, that is differentiation, right? We can do differentiation at that point and we get a derivative at that point, right? So given a point, we can assign a unique derivative at that point, right? So we get a function. So the function defined on all points where fx have derivative is called the derivative function of f of x, which is denoted by f prime of x or dy of dx. So f prime of c and f prime of x are the notation invented by Euler, an 18th century mathematician. Dy of dx, okay, is invented by Leibniz, okay, whom we mentioned at the start of the course, right? So, okay, with these notations, the tangent of the tangent of the gradient of tangent, right? The gradient of tangent, this notation, right? By our definition, it's called the differentiation, right? The gradient of tangent, right? So it's denoted by f prime of x of f prime of c, right? So we can change this notation into f prime of x, right? So the expression comes like this. Or depending on your preference, dy over dx becomes like this, right? Okay. Something to note here. The first thing is that x can never reach zero. Okay. Why? Because as you can see, this part is a gradient of second line. So the second line connecting 2 points, right? So if we go back to our definition, we can see it's delta x means a change in x, right? Since the 2 points are different, right? So the delta x can't be the same. Delta x, so the 2 points can't have same coordinate. That is, delta x can't be 0. It can only get closer and closer to 0, but not 0. The second is a limit is with respect to delta x, with respect to change in x. So some students may okay, just keep in mind this in terms of x. Okay, it's not in terms of x, not in terms of other variables. Some cases students just keep in mind, okay? The third thing to note is that delta x is not delta times x. It's as a whole means the change in x coordinate. Okay. The fourth thing to keep in mind is that our operation is carried out in two steps. The first step is a quotient operation. After until you can't, it can't be simplified, then you turn to limit operation. So just keep in mind the order of operation. Okay. Now we turn to examples. First example is find the derivative of f of x equal to x squared at point 2, 4. Now the derivative, this is derivative of a function at a point, right? So a derivative of function at a point by our definition is denoted by f prime of c, right? So here c is 2, x coordinate 2, right? So it can change into, can writing into f prime of 2, right? And by definition, so f prime of 2, as we already learned, is a gradient of tangent, it's a differentiation, right? So by definition, first, find the gradient of second line, right? That is delta x over delta y, right? Then followed by limit operation, that is related to the second line, get closer and closer to the tangent line, right? That is related delta x approach to 0, right? So keep in mind the limit is with respect to delta x. And then we start with the quotient operation, right? We do substitution. F of 2 plus delta x becomes 2 plus delta x squared minus delta 2, minus 2 squared, sorry, over delta x, right? And since it can be simplified, right? So, for example, we can expand the bracket, right? So it becomes like this. And then it still can further be simplified because 4 and minus 4 can cancel with each other, right? And at this step, we have delta x on the top and delta x on the bottom, which can be cancelled, right? Which cancel with each other, right? So it becomes, after simplification becomes 4 plus delta x, right? So now 4 plus delta x can't be more simplified, right? Okay, so now we turn to the limit operation. Now keep in mind our limit is with respect to delta x. And also keep in mind that delta x not delta times x, okay? So after applying limit to 4 plus delta x, we get 4, right? So finding the derivative of a function at a point is just using the concept of differentiation, right? So take care, you really understand the two-step process, okay, in differentiation. Now, second example, find the derivative function of f of x equal to x squared. Now, this time, we aim to find finding the derivative function, okay, by our definition. The derivative function, okay, f prime of x, which goes like this, right? It's two steps. The first step is gradient of second line, right? The second step, we let the gradient, the second line goes approach to the tangent line, right? And that is delta x approach to 0, right? So it go like this. Sorry, go like this. Now this time, some we can replace data x by h. It doesn't matter. You can, if you like, you can use data x. But once we fixed the convention, this part must be in line with this notation. That is, if this part is h, then you can't use delta x approach to 0, right? Okay, understand? So just keep consistent. Consistency is very important, okay? So now we start from the quotient operation, right? And we do institution. We replace f of x plus h by x plus h squared and f of x by x squared oh, and then we expand bracket, right? And we do simplification, okay, until here. Now, at this step, 2x plus h can't be more simplified, right? So we apply limit operation. Be careful. Some students may apply limit to x, okay? Always keep in mind, our limit is with respect to a change in x, okay? Which is h here, right? So our result is 2x, right? As h goes to 0, right? So again, this is application of two-step two-step differentiation, right? Now, this is our in-class exercise. Now, two students will be required to operate on the blackboard. Others, please finish on your own, okay? And we will mark your answers. We will mark and read your answers, okay? So what have you learned for today? So we have learned the two-step definition of differentiation. The first step is draw second lines and figure out the gradient of second line, right? The second step is we let the second line approach to tangent lines. That is, we let delta x, the change in x, approach to 0, and we apply the limit operation. Okay. So all your assignments, these are your assignments, which were all based on your understanding in differentiation. So if you have any further questions, please feel free to consult me, okay, in my office. Okay. Thank you. So class is over. Bye bye.